Hello and welcome to a different kind of video. This will be more of a lecture type. It's going to be an interesting experiment for me because I'm usually not a lecturing kind of guy. But I'll be talking about balanced string gauges for bass guitar, since I had a conversation over the phone with a fellow bass player who actually got me into playing, but it's beside the point. We'll be looking at the basic physics of waves, just a rough overview, sound waves. And then we're linking the sound waves to the string vibrations. Then we're going directly over to the physics, the properties of the bass string. First, a real fundamental view of physics of waves. You know the formula, speed is distance over time. It's the same with sound waves. It's just the speed of sound equals the wavelength times the frequency. The sound is usually produced by forced vibrations and dampening in the speaker. But we're not solving differential equations here. We're not interested in this. We want easy to digest stuff. There are 12 notes in the equal temperament tuning. All pitches are the exact distance apart. A440 is the standard pitch, which means the A4, or the one-lined A, is tuned to 440 Hz, and all the other notes are just same amount of steps away. So I early on used the MIDI standard. This quick formula on the bottom gives me the frequency of the note. As an example, the low string on the violin, the G3, is exactly 196 Hz. And you can read it yourself, the E1 low string on a standard tune bass is 41.2 Hz and a bit. The human hearing goes from about 20 Hz to 20 kilohertz. So I've talked a lot about sound waves. Yeah, sound waves are longitudinal waves or compression waves. What you hear is air pressure moving your eardrums. What the bass string does, it vibrates transversal, so there's a transversal wave going through the string, which is picked up by the pickups, turned into a tiny electrical signal that's then amplified by an amplifier and then pushed out as longitudinal waves by the speakers, which gives us a nice transition into the physics of bass strings. Again, speed is distance over time, so the wave propagation speed is double the string length times the frequency. Our frequency of our string is the modes divided by 2 times the length times the wave propagation speed. So the next question that arose, what's the speed of the wave in a string? We can describe it by the square root of the string tension divided by the linear density. See, I'm not that into linear densities. I like to have 3D objects when I'm looking at the properties. So I quickly converted the linear density to cubic density. So now we're looking at the string properties by string radius or string diameter and material density, which gives you a much firmer grasp on the situation. Next, we're ignoring all the harmonics, just looking at the open string and its fundamental. So we say n equals 1, and then our frequency formula looks like this. We have the string length, the string tension, the string diameter, and the material density. As I wrote here, we usually know what frequency we want to tune our strings to, so let's rearrange the formula to get the string tension. You can here see the string tension is frequency times length times diameter, all this squared, times pi, times the density of the material. But if you have a certain tension in mind you want the string to have, and you want to figure out the string diameter, you can rearrange it like this. The string diameter is the square root of the tension divided by pi, density, frequency squared, and the length squared. Just a heads up, all the measurements I've used are taken in SI units, so if you plug in SI units into the formulas it all works out perfectly. Here's some assumptions. So the real string is made up of a core and winding, and what I've been presenting up till now is string is made up of a really long 100% dense cylinder. We know that the density of iron is about 7.8 grams per cubic centimeter, stainless steel is about 8, density of nickel is about 8.9. But if we want a density of real strings made up of steel or nickel, we have to bear in mind that string is not 100% dense. Because of the winding, we have a few gaps in the string. If you look at it like this, those pockets vary by the thickness of the wiring. So the actual density of the string is depending on the core thickness and the wiring thickness. And I've looked up some manufacturing websites. The density varies wildly between different string gauges. So different manufacturers use different core thickness and wiring thickness for the different gauges, and it totally makes them not comparable. The thinner strings are always denser than the thicker strings. So I took the average of the D'Addario and GHS steel strings and fitted a linear curve through all those numbers for my following calculations. We can finally get into some string gauge examples. I'm using 4 sets as an example. For standard tuned bass, it's usually 100, 80, 65 and 45 milli-inch. We get to following tensions, as you can see here. And you immediately notice that the lower tuned strings have less tension. So my immediate approach was to reduce the string diameter to reduce the tension on the really hard strings. There is also another manufacturer that produces balanced string gauges, and if you plug their numbers in you get a really balanced set, but the string diameter is pretty exotic. And for comparison, here's the set I'm currently playing. Next, an example that really drove me nuts when I strung up my ESP and tuned it down to low A. So here we have the set you can buy in store for a 5-string 35-inch bass, 135, 105, 85, 65 and 45 milli-inch, which results in a really imbalanced set where the lowest string keeps flapping around while the C and G strings are tense and really hard in comparison. So I went back to the store and asked if they had a 140 milli-inch string, and they said no, they're not making those. When I looked online, again found a certain brand of strings with balanced gauges, really exotic gauges, but turns out those gauges are like they advertised, really balanced. But I took a different approach and I made up my own balanced set from just not looking at any numbers, just going by feel, and well, came up with this. It's not only balanced on paper. I've been experimenting with string gauges before I picked up the calculator and started calculating. I just went by feel and said, this string feels a little stiff, I want something looser here. This string feels a little loose, can you crank up the diameter? And that's how I ended up with my current gauges. Last, and the real reason why I'm making this video, is the guy that called me. He's tuning to drop C on a 34-inch 4-string bass. He always buys a 5-string set, and he allegedly throws out the thinnest string and strings up his instrument with the other 4. That's the first column you see. The tension is really high, the strings are really stiff. I still don't know how he manages not to break the F string, because there's almost 38 kilograms resting on the string, while the low C string is only about 18.5 kilograms. That's nuts. What I told him would be more reasonable is to throw out the second string, the 105 milli-inch, and string up the bass with the rest. So he has the really tense, the really stiff 135 for the C, and the rest as follows. I've been talking to another colleague at university. He played drop C in a metal band, and he was using the following set, which is kind of balanced for G1, C2 and F2. What I would recommend for a guy who likes his tension at about 18.5 to 19 kilograms is a set of 135, 90, 65 and 50. What you should take away from this video is, if you play a different tuning, just don't buy a standard set of strings and think that it's going to be optimal for your setup. Just take the time, look at different gauges, maybe experiment, look what feels right, and it will be much easier to play and have fun. As far as sources and references, I've listed here. I want to give a special shout out to Pyramid Strings, especially for their patience when it comes to my orders. Thanks for watching, and have fun playing. Bye.